Hello. Every year, millions of liters of industrial water are released into the environment. These wastewaters are loaded with heavy metals, rare earth, and pharmaceuticals and other emerging contaminants. But what if this waste wasn't waste at all? What if it could become a resource, a hidden treasure powering the technologies of the future? Hello everyone, welcome to Clean Copper Talks. Today we will explore how scientists are recovering critical minerals from wastewater, transforming pollution into opportunity, and how this innovation could reshape our clean energy journey. So stay till the last. Critical minerals are elements that are essential for modern technology and green energy, but they are scarce, hard to substitute, and concentrated in just few regions. Example: lithium, cobalt, nickel, and graphite are vital for electric vehicle batteries. Similarly, rare earth elements like neodymium and dysprosium used in magnets and wind turbines. Similarly, gallium, germanium, indium, these are critical for semiconductor and solar panels. As we move towards net zero emission, demand for these minerals is skyrocketing. By 2040, the world would need 40 times more lithium than we use today. But traditional mining is energy intensive, polluting, and geopolitically risky. For instance, China controls over 80 to 90% of rare earth processing, and that's why researchers are turning their attention to an unlikely resource: the wastewater, a hidden reservoir of the valuable materials. So, wastewater might seem like something to get rid of, but it is not really. It is a liquid mine rich in trace minerals. The key resources or key sources in a wastewater are industrial effluents. It includes electronics, metal plating, battery manufacturing, chemical industries discharge, and these wastewater contain nickel, cobalt, lithium, manganese, and rare earth. Similarly, mining and oil field wastewater, acid mine drainage are abandoned mines which carries iron, copper, zinc, and rare earth elements. Oil field produced water, especially from the shale formations, can contain up to 100 milligram per liter of lithium, which is comparable to natural brines. Similarly, municipal wastewater, everyday products, detergents, cosmetics, e-waste residues release tiny quantities of gallium, indium that accumulate in the sewage sludge. So instead of being a liability, wastewater can be a sustainable source of critical minerals if we have the correct technology to recover them. Now, there are various technologies for recovering critical minerals. Recovering metals from the wastewater requires innovative chemistry, material science, and biotechnology. Let's break down the key methods being explored globally. Chemical precipitation. This is simple and effective. Chemicals are added to adjust the pH and form insoluble compounds like nickel and chromium hydroxide. Commonly used for nickel, manganese, zinc. Advantage that is it is easy and low cost, but it has limitation. It produces sludge, which needs further treatment, that means further costs. Second process, ion exchange. It uses resins or columns that swap harmless ions like sodium with metal ions. It can selectively recover chromium, cobalt, or lithium. This is highly efficient but requires regeneration chemicals, which is again cost. Adsorption. Perhaps this is the most promising technique. Adsorbent materials like activated carbon, biochar, zeolite, and graphene oxide selectively bind metal ions. For example, biochar made from agricultural waste can capture up to 90% of the rare earth from industrial effluent. Example, uh, s- this is sorry advantage, this is simple, regenerable and eco-friendly. Membrane and nanofiltration. Nanofiltration, reverse osmosis, electrodialysis, all used to separate and concentrate iron. Advanced ion sieving membranes can selectively pass lithium ions while blocking others, ideal for geothermal or battery wastewater. Electrochemical methods, techniques such as electrowinning and electrodeposition use electric current to plate metals onto electrodes. Electrocoagulation creates flocks that trap metals, removing over 90% of the nickel in same battery studies. The benefit of this method is it gives direct recovery and minimal chemical are used. Biological recovery. Nature offers sustainable solution. Biosorption uses microbes, algae, or cyanobacteria which binds metal onto their surface. Then bioleaching. Bacteria like Acidithiobacillus extract metals from solids by oxidation. Bioprecipitation. Microbes convert dissolved metals into insoluble sulfides for easy separation. These processes are energy efficient and eco-friendly, sustainable for low metal wastewaters. Hybrid and advanced process approaches. This method enhances the performances. For example, membrane filtration followed by bioleaching or adsorption followed by electrodialysis. Further systems may integrate AI-based sensors to detect metal concentrations and automatically trigger recovery cycles. So what the global research and real-world case studies are looking for? This is not just a lab concept, it is really happening worldwide. In United States, DOE backed projects extract rare earth from from coal ash and acid mine drainage. The Salton Sea Lithium project aims to produce 25,000 tons of lithium annually using direct extraction from geothermal wastewater. In Japan, since 2017, pilot plants near Tokyo recover rare earth from sewage sludge ash, a major step towards circular economy. In Germany, membrane-based systems are being developed for lithium recovery from geothermal brines. In India, IITs and CSIR labs are researching adsorption and photocatalytic recovery of rare metals from industrial wastewater and e-waste leachates. Space research. Even NASA studies closed loop recovery system for further long duration missions, proof that wastewater resource recovery is frontier technology. Now the environmental and economic benefits. Recovering minerals from wastewater is a double win for environment and economy. The environmental benefits are it reduces heavy metal pollution and protects aquatic system, minimizes the need for new mining, conserving land and reducing emissions. The economic benefits are that it turns waste into profit. Wastewater plants become resource recovery hubs. It helps nations to reduce import dependency for critical minerals. It creates new green jobs and supports local industries. The circular economy impact it has that instead of linear take make waste, recovery technologies create a looped system where waste from one process fuels another. Now, what are the challenges and road ahead? Like every emerging technology, this field also faces challenges. Trace concentrations. The concentrations of these critical minerals are often in microgram per liter, which demands ultra sensitive systems. Sophisticated and expensive systems such as HPLC, HPLC, MSMS. Then selectivity. This is hard to isolate one metal from many competing ions. Then the cost. Membranes and adsorbents can be expensive or difficult to scale. Then there's data gaps. Limited monitoring of trace elements in wastewater has been there, so the data is not available readily. However, progress is rapid. With innovations in magnetic biochar, MOFs, and graphene membranes, plus AI-driven process optimization improving efficiency. Government are also supporting pilot-scale demonstrations and including critical mineral recovery and sustainability policies. So, what is the future vision? Smart wastewater plants that detect, capture, and recycle valuable elements automatically contributing to both clean water, and clean energy goals. So, recovering critical minerals from wastewater isn't just an environmental fix, it's an economic revolution. It determines waste as a resource, pollution as potential, and scarcity as opportunity. In the coming years, the line between wastewater treatment and resource recovery will blur, leading us towards truly sustainable cities and industries. So, next time you see wastewater flowing, remember it might just hold the metals that power our future. If you found this video informative, hit that like button, subscribe this channel, and share this to spread awareness of sustainable innovations. This is Clean Talk Copper Talks, where science meets sustainability. Bye bye, take care.